Okay, see, in the last class we talked about the equation of motion that we have derived. Okay, I will just write it down, just the sway and all, or maybe because to start it we always have to write. See, these were what we wrote yesterday in last class as the linear dynamic equations of motions in the horizontal plane. Okay. All right. So, this is my, the first one is so called surge equation. All right. Next one, sway equation, and this one is my yaw equation. All right. So, we had got here 3 modes of motion x, y, z. So, sometime you may call this to be linear dynamic equation of motion in the horizontal plane. I would write 3 degree of freedom, by meaning here I have got only 3 modes where I am allowing the shape to move. Why I am saying, this is the simplest one that you have to have. You could also have little more complicated one. For example, if I allow the shape also to roll, because when it turns it might also roll, then I would have had one more equation here, would have been roll equation of motion. Then I would have had 4 DOF equation of motion, etc. So, I could have more complicated equations of motion. Now, what I mentioned yesterday, if you look at that, the important part in this equation of motion, the part that consists of hydrodynamics of the hull, arises in, I will only look at sway and yaw equation primarily, because this equation is of relatively less importance for us. See, here it is terms like this, terms like this, terms like this, terms like this, then it is this, this, this. So, we have these terms, and I mentioned that. What does these terms mean? They basically means the rate of change of forces or moments y or n, that is d of y or n against d of v, v dot, r, r dot. Rate of change of the sway force or yaw moment with respect to sway velocity or sway acceleration or yaw velocity or yaw acceleration. What it means is that I have a hull now I am trying to give it a velocity here v. Okay. What we want to look is that supposing the ship is going, see what means, that means that the ship is actually going with this velocity vector here. So, the question is, that means it has got a component of velocity this side. What we want to find out, if suppose there is so much v, what is the corresponding y, what is the corresponding n. So, suppose I could measure, say for a given v, for whatever v, this is y. So, if I could measure v versus y arising only because of v, let us say some kind of a graph, then this slope would be my dy by dv. What does it give me? If I call this, that is that means if I want to find out some value y at v, then it is going to be dy by dv into v or yv into v. This is the approximation with a linear approximation of the force. So, these terms, you see, these terms which are hydrodynamic forces, rate of change of hydrodynamic forces or moment, rate of change of hydrodynamic forces or moment against any of the velocity parameters, these terms are known as hydrodynamic derivatives, because they are hydrodynamic derivatives, derivative of the hydrodynamic forces and moments. So, you see these terms, that is d of d some people call them also coefficient. Some people sometimes call them also hydrodynamic coefficients. See what happens, this is a very important concept, you know. That means I have a given geometry. Now, I am trying to give it some kind of acceleration in some direction. I will come to this term by term, we will see this magnitude, etc. Then it obviously, then certain hydrodynamic force is created, obviously that will depend on geometry. Suppose you take a ship, a particular geometry, if I give a v, regardless of it is whether today, tomorrow, day after, it will give so much of y. So, dy by dv will become intrinsic property of the hull, that is the characteristic of the hull. Okay. Once again I will come to that. Suppose I have a given geometry. Okay. Now, in that given geometry, say design number 1, I give it a certain velocity v, it will give you a certain y. Now, dy by dv, that is per unit y, the amount of v by the amount of y that comes out will remain same for the hull, that is the characteristic of the hull. That is, for example, if you have a hull, now if it was having a draft of say 5 meter, it is going to have certain kb, okay, center of buoyancy. Now, that kb is a fixed for that hull. If it is having 5 meter draft, it will have so much of kb or so much of bmt, regardless of you know what you say. So, that becomes a characteristic of the hull. Okay. So, hydrodynamic derivatives therefore Why I am saying this, because just like certain parameters like hydrostatic parameters for a given geometry, remember when I give the example of KB at 5 meter, remember at 5 meter draft the underwater hull geometry is fixed. So, for that geometry there is a fixed location of center of buoyancy. Similarly, if there is a given geometry, you obviously, if that given geometry, if that has got a certain amount of V, then it will have certain amount of Y. That means its rate of change of Y against V will remain constant. So, these things therefore characterizes the hull. Added mass, we will come to this added mass etc. in a minute, they are all characteristic of the hull. Okay. So, this is what called the hydrodynamic derivatives. Now, how many we have got? Remember, I in this two planes I have got Y, I have got N, this side I have got V dot R dot. This is velocity, acceleration, right. So, I have got, if you look at that, I will come back to that, I have got YV dot NV dot YR dot NR dot. These are the 8 linear derivatives that we had. If you look at this first, here you will see this, there are 8 there, 1 2 3 4 5 6 7 8, very important 8 derivatives. Okay. That is obvious, because I am talking of 2 motions, forces y and n, and 4 velocities. So, 2 into 4 gives you 8, of which just for definition purpose, these 2 are linear velocity derivatives. Linear because V straight line velocity and R is rotational velocity. So, you can say then these 2 you can say are linear acceleration derivative, right. These 2 I can say are angular velocity derivatives. Okay. And these 2 are going to be angular acceleration derivative. What I am meaning, therefore, see, I have got linear velocity, this one. So, YV NV, this is linear acceleration, this is angular velocity, angular acceleration. Why I wrote is that this is only for your convenience, you can therefore find out. Then if I want to call more generally velocity derivative, then of course these are velocity derivatives, and if you take acceleration derivatives, these are acceleration derivatives. So, I have got basically, again if I want to say that I have velocity derivatives, I have got acceleration derivative, which these are linear velocity derivative, these are angular velocity derivative, etc. Now, I will like to discuss this term by term about their magnitude, are they positive, are they negative, etc. But remember why it is important, because see, if once again we go back to the equation of motion, obviously it depends on the we need to know whether they are positive, negative, etc., because this has a bearing on how the equation of motion will have a solution. just like your metacentric height should be positive. There is a condition that comes out for stability purpose. So, we of course need to study this, because the unknown part is in this red marks, these derivatives. The rest of the terms are only mass property. See this m, center of gravity location, mass distribution, moment of inertia. So, rest is basically mass and moment of inertia and CG location. Okay. So, the hydrodynamic comes only in this. That means the unknown hydrodynamic forces that has got created on the hull are fully represented by these 8 terms in this equation of motion. Of course, if you take more complex equation, it will be more, but to start with, the basic minimum unknown becomes this 8, provided there is no rudder action. I have not taken a rudder action, rudder is not working, it is only a bare hull. Okay. Now, let us look at the terms, but before that let us also look at this physics. See here I have this term m minus y v into v dot. I will just look back at this term, this m minus y v dot into v dot. So, I have this acceleration term becomes m minus y v dot into v dot. Compare that with what we did in sea keeping. In say in heap, this is in sway mode, right. So, essentially this is m minus y v dot into this is y double dot, like, because if I call x y z to be displacement, in analogy with that, see in heave my inertia force was mass plus added mass into z dot dot. So, if you compare that, what do you find? You will obviously find that this term, this is nothing but sway added mass with a negative sign. Now, similarly, if you look at this I z minus n r dot r dot, this term I will write it here. Which of course is now you see in the pitch or roll, say in pitch equation I had I y y plus delta I y y into theta dot dot. What do you find? What was this? This was my pitch added moment of inertia. So, obviously, what happened to this? This is equivalent to added moment of inertia, right. So, you see what I mean is that some of these terms are actually same as added mass, added moment of inertia that we have seen. Again, added mass, added moment of inertia are also intrinsic property of the hull. Okay. So, we now understand this. Now, why I am saying is that therefore, what happens that these terms, these acceleration derivatives, this essentially becomes what we call added mass forces. And of course, I can call them to be damping forces, but this damping is not same as the damping that we have had in free surface. Okay. So, but this added mass is same as in the case of sea keeping. I can call this to be damping forces, but I am very kind of hesitant to call that so straightforward, because you have to understand that in sea keeping I had added mass and damping. That damping arose because of free surface waves. because the ship created waves, but in this case they are not creating waves, and the phenomena of this force is not same as that damping. In other words, there the damping was called radiation damping forces, means that is what we call them in seakeeping. Let me write it down here, otherwise you will have confusion. So, we have got C. They are not forces, they are basically this multiplied by respective velocities v dot r dot, that is what you get arrayed mass forces and moment. Damping see these are dot here, but only thing I want to tell you is that in seakeeping what we studied, damping forces I am just writing that different origin. You know the why I want to tell you is that essentially in fluid mechanics, this is another thing that you should understand. Essentially in fluid mechanics, any force that is proportion to velocity, that means any force that you write something into velocity, you normally call it damping force. The word damping is a very generic term. You know, if it is proportion to inertia, acceleration, you call inertia force. See, in any equation of motion, mass into any force in proportion to acceleration is called as inertial force. Any force is in proportion to velocity is called damping force, and any force in proportion to displacement you call stiffness or static force. So, here because of the nature we are calling damping force, but this damping force should not be confused with the seakeeping damping force that we have done in the first part of the course. Why I am saying? Because the added mass force remains same, but the damping force does not remain same, that one must recognize. Okay. So, this we can keep going on, but let me now go to one interesting point. Let us take term by term to find out their magnitude, where they are positive, where they are negative, what happens, etc., etc. Okay. This is very interesting. Now, let us take V. So, I have this body here. Now, I give a, see, remember this is my direction, right. Now, let us take one by one. Suppose I accelerate the body this side, plus side, remember this is plus side, this is of course minus side. See, positive axis, no, this is plus x, this is plus y, and this is what we are calling this side plus psi or theta, whatever, plus r. Let me rather put it plus r, x to y direction. That is the axis system we chose. Okay. Now, you see what we are doing, we have to pay attention to this now, you know. Now, I am giving, I want to find out, there is a graph I am putting. Let us take first y v dot, v dot, okay, v dot and v. So, I am giving a v dot plus v dot, okay, means I am accelerating the body this side. I want to find out which direction and about how much y will come. Now, you tell me, if I were to push it, accelerate it this side, what would happen? The resistive force, if now remember I am accelerating this side, the forces resisting will all come in this side, right. if I then that means ultimately what I will get is y will be this side. See, if I want to push the body this side, which side the force will come? Fluid force on the other side. So, if I give a plus v dot, say I am accelerating here, I will get a minus y. So, if I get a plus v dot, I am going to get a minus y. That means I am going to get a value somewhere here. That means the graph will look something like that, or rather let me put a different color. And if I get a minus v dot, obviously I will get a plus value. So, then what happened? This is y. So, what happened to y v dot is always negative. So, that actually minus y v dot is always positive. Okay. In fact, that makes sense, because minus y v dot is the added mass, as I have just found out here in earlier talk. Minus y v dot is added mass of course is positive. Okay. So, so interestingly what you find out, y v dot is always negative, that is 1. How much is the magnitude? Now, added mass is in this mode, that is you are pushing the hull this side, entire hull. So, if I were to look the cross section of the hull, let me put that way somewhere here. This is my draft T, this is my, if I swayed it, there is basically it is added mass, it is essentially same as the mass of the fluid being accelerated. So, this mass is going to be almost same as the mass of the hull itself. This we have talked. See, now how do I explain that? See, if I took this pen here, okay, in heave, you remember when I said when I push down, the entire bottom part of the particle gets pushed down. So, the mass of that added mass becomes almost like semicircle added to this length. So, this if you do that will become almost same as the mass of the hull itself. So, if you do the same thing this side, here we are doing this side, same result. There it will be the bottom surface pushing the water, there it will be the side surface, that is the T surface, that L by T, that as if this much is being pushing. So, it is going to be essentially similar to some kind of a I will tell that like water mass of this semicircle or whatever, like this semicircle, almost like this mass. That means added mass in sway is almost same as the mass, or rather this is more or less order of mass. Why I am saying this? Because that means it is very large quantity. After all, mass of a hull is very large quantity. So, this is a large negative quantity, not y v dot. Actually, y v dot into v dot will be, actually this is not okay, this is like a mass, sorry. So, y v dot itself is a very large negative quantity. Okay. So, this we have done. Now, let us look at y v, v versus y. So, the same thing will apply if I were to give it here a v, not in acceleration but velocity. What will happen? The fluid is going to give a push on this side, right. So, what will happen? You are going to get again a graph which will look, for a positive v I get a negative y, for a negative v I get a positive y. So, I am going to get something like that. Again y v will become, it is also fairly large, may not be as large as this, we do not know, but it will be a negative quantity, moderately large, I can say moderately large. Okay. So, you see that means now always so, see this is universal, that means y v and n y v dot are always negative. Now we will come to NV and NV dot for the same V. Okay, we will try to see this NV and NV dot. We'll see whether. We will, before that NV, let us look at this YR then. I mean, like we'll take one by, see we have got 8 terms. We need to go slowly one by one to find out how they are. Okay, so this is with YV and all. Let's look at this now. Here actually, let me write it down. This Y versus, that's what we have done. This is Y versus V dot. Now we will do Y versus R dot. We will try to see, that means dy by dr, dy by dr dot. Let us see how they look like. Again, so I am basically turning it. Basically I give a plus r. Remember, this is plus r, this is plus y. V is not there, so we do not care. Remember, when we do YV, YR, etc., which means I am trying to evaluate for only that particular motion, only for V what is Y, only for R what is Y, that is what we are doing. So, here I have to give it only R. What is R? Turning it. So, I turn it. What happens here? See here. If I turn it, fluid pressure acts on this side, and here fluid pressures act on this side. Right. So, let me call this Y stern. This is Y stem. So, what happens to my Y? Y is Y stern plus Y minus Y stem, because remember this is my plus Y direction. Once again let me see, this is my plus Y direction, Y stern is plus, Y stem is minus. Now or rather, well, let us first talk R dot part, right, R dot part instead of R, same thing, R dot R will remain same. Okay, if I talk R dot part. Now you see, if Y stern is larger than Y stem, then what would happen? It will become positive. So, this graph will become, see here I put in this R dot, it will become right. But if opposite happens, it will become like that. So, in this will give me in fact, I can make it R dot both. Because now the same thing will happen, I mean whether this is Y. What, now the point therefore is that, see, as far as Y against R or R dot is concerned, okay, that is another interesting thing. Y and R, this I will come afterwards. When it comes to Y and R or R dot is concerned, half the hull produces Y in one direction, other half of the hull, or half means aft part, on the other direction. Now, so therefore, it is like large number minus another large number. The final number is a small number. So, first of all, the values of these are small, number 1. Number 2 is that whether they are positive or whether they are negative, that depends on whether stern is more influential, that means stern is dominating, or stem is dominating. For example, This is why I will tell you an interesting point. Suppose this CG point, if you make it move forward, okay, what would happen? Stern will become more dominating, and therefore it will become more and more positive. You agree with that? See the physics, you see, if I were to shift this point of rotation here, if I were to shift the point of rotation here, what happens? The stern part becomes more larger. So, the stern becomes more and more larger number. So, therefore, this will become more and more positive, or even if it is negative there, suppose there is a hull, I had my yr dot negative. If I shift my CG forward, it will be less negative, going towards positive. Okay. So, what our conclusion? yr dot positive or negative, depending on the which is better, it can be both, but small, relatively small value. Relatively small value compared to the yv dot that we have done. Okay. So, this we have done now. Now, we are going to look at the n part, that is, now we will see n versus v dot. Now, remember here I am giving again a v dot, same thing. So, what happened? I have got here forces acting this side. What will these forces do? These forces are going to give me this side, forces are going to give me this side n. See, I am pushing this body this side. So, the fluid forces are acting along this line, right. Now, I am trying to find out n, the moment. Remember, this is my plus n by axis, because this is my x, this is my y, right. Now, you see, this part of the hull is going to give me moment this side, this force gives me moment this side, this force is going to give me n stern. So, the net moment n is again n stern minus n stem. Agreed. So, this will apply to whether you give a v or v dot. Okay. So, then exactly the same thing is going to happen. So, if I were to now plot v dot, I mean I am taking both of them together, one could take probably separately. Now, what happens? See, if n stern is more than n stem, then I am going to get a positive value. If this is again dominating, n stern dominates n stem, then it will be this n. Or it is going to be like that. So, the conclusion again, NV dot can be positive or can be negative. That is agreed, right. So, we end up having also this conclusion. Now, comes the final one, that is n versus r dot. This is little more again I have this hull. Now I am, remember, giving a rotation of r plus r. This is plus r. What happened if I do that? This side my fluid force is acting this way, and this side fluid force is acting this way, because it is trying to rotate, right. So, what this is going to do? This is going to give me, this side force is going to give me a moment this side, that is n stem, and this is going to give me a moment this side. That is true. So, therefore, my net n is going to be negative, because it is going to be this side total n. Agreed. See, if I were to rotate it this way, this giving force this side, this giving force this side, this giving moment this side, this giving moment this side, both of them are going to give me moment this side. That means, when I try to turn it here, I get a moment this side. When I want to turn it this way, I get a moment this way. This part again gives me, see, you can imagine there is a net force here that gives me moment this side, and there is a net force here that will give me moment this side. So, I am going to get a large, because both forward and aft side gives me moment of the same direction, they get added. So, therefore, what I will get, if I give r dot, then I am going to get always in fact nr dot, we have seen in earlier, I just explained here, minus nr dot is yaw added moment of inertia, just like pitch added moment of inertia. In fact, it will have a magnitude or this thing of almost mass into radius of gyration square, which is something like 0.25 L, very large negative number. So, we end up getting the same thing. But this may not be very large, maybe because it is a velocity derivative, it may be moderately large. So, you see, we end up getting this conclusion, that is very interesting. Now, I am going to just summarize these conclusions now. So, what I end up getting here is, now see why I am taking time, because this is very important, because these magnitudes actually will decide the characteristic of stability of the hull that we will talk in the next hour. See, y v n v, y r n r, y v dot n v dot, y r dot n r dot. Now, I will also write this thing. See here, remember direction x, forces here is y and n, that is x, sorry, y direction and z direction, moment z direction. Now, in y direction velocity here is v, and z direction velocity is r. Okay. So, this is basically v and r. If I write why I am saying, basically you will see similar will happen y z y z. If I write acceleration, this y n and sorry this y n is here. If I write here y and z here, this is v dot r dot r dot. You see y v dot, and therefore, this term, therefore, what I am meaning is that the term becomes like that, y v n v y r n r. It is like a diagonal term here, because this is actually y axis, this axis, and here y v dot n v dot y r dot n r dot. I will tell you what I meant by that. See, y force is the force in direction y in which the velocity is v. So, y v is the so called diagonal term, means you are trying to find out force in the same direction in which velocity is taken. Once again let me explain that. YV is force in the direction y with respect to, or gradient of that with respect to motion in direction y, that is dy by dv. Once again, yv represents force in direction y, d of force in direction y divided by d of velocity in direction y, both are in y direction. So, dy by dv, whereas dy by dr would be force in direction y divided by, or rate of change against motion about direction z, because r is that. So, that is y and z. This one nv, moment in direction z because or due to velocity in direction y, dn by dv. This is motion moment in direction z because of motion moment in direction z because of motion in direction z. So, that is why these two are the diagonal terms, so called. If I write here y z, this side the forces, this side the motions, these two are diagonal terms, these two are cross coupled terms, because they represent force or moment in direction one direction due to motions in another direction. Do you understand that? It is force in one direction because of motion in another direction. So, these two are my diagonal terms, and these two are my cross diagonal terms, cross coupled terms. Okay. So, these rates are diagonal terms. Of which these two are added mass terms. This is actually sway added mass with a minus sign, minus of sway added mass, minus of yaw added moment of inertia. Why I am saying that? Remember, these diagonal terms turns out to be, if I look at these two diagonal terms, yv dot nr dot, large negative. Even these two are negative and fairly large. Okay, I am not putting the large part, yv and nr. Okay, that is what we have found out in all these parts that we have gone through. If you look back now in our going step by step, see yv dot is always negative, yv also, well, yv dot is always negative, yv is also negative, yv dot is always negative large, yv is negative. Okay, we have done that. Then look at this, yr dot can be positive or can be negative, but small values. So, y r, let me put a different color, and y r dot. Okay. Then we had if you look at that nv dot, again it can be positive or negative, but small value. And finally, we had got nr dot negative, which I of course wrote nr dot negative large and nr negative large. What do you find? Interestingly, what you find, these cross diagonal terms are always positive or negative and small value. The diagonal terms are always large values. It also makes sense because diagonal terms are always negative. What it means by the diagonal terms? That is force coming in a particular direction because of the motion in that direction. So, if I want to go push it in this direction, I will always get a force opposite direction. If I want to rotate in plus r, I will get always moment in opposite direction, right. It is like your stability. If I want to give a theta this side, I get a restoring moment opposite side, coming because of diagonal terms. Unfortunately, here we have also cross diagonal terms. Okay. So, anyhow, so this is what we should remember. So, this is a very important and interesting point, of which, as I told you, these terms are added mass terms, these are damping terms. Added mass terms are inertia forces, these are forces because of velocity. We do not yet know necessarily, or rather I can say that understanding of these forces are more known. However, we will find out in the next class that importance of this is much more as far as maneuvering is concerned. In fact, maneuvering characteristics, stability characteristics will be decided by basically these quantities. So, with that I am going to close this hour of lecture. In the next hour we are going to talk about the directional stability concept, that is what it takes for the ship to be directionally stable. What should be the criteria? The same question that we ask, that when I throw a particular arrow, it goes on a straight line provided I put a mass on the forward side and a feather at the end, which is what every tribal person knows and when they are making bow and arrow. Okay. The same thing we will discuss, find out formally. So, with that I will end today this hour of lecture. Thank you.